Hello, everyone. So, welcome to the tutorial on JavaScript. Just a quick note, if anyone's having any audio visual issues, there should be a little like button at the top right that says help. If you're having any issues with that, then you can just click on that and it should help you troubleshoot that. And so let's talk about JavaScript. But before that, let me actually introduce myself. I am Tav, and I'll be your host for today. And I'll be talking about data structures and recursion in JavaScript. Just a quick note. In JavaScript, the data structures that are built into the actual language are like not that extensive, to be honest. So it's mostly just arrays. But the important thing to note about this is that Java data structures are just an important concept altogether. Like, even though they are not built into the actual language itself, as compared to other languages like Java or C Sharp, for example, they are important to know, as interviewers will ask you about them, and also it will make your okay, we'll get into that, but basically it just makes for a better program if you know how to use data structures effectively. Okay, so I just want to test out this screen sharing and also run a quick demo just to show you my environment, the environment that I'll be using to do some examples later on. Let me just enable screen sharing real quick. Okay, well, it's a bit trippy, but hopefully you can all see my screen now. And the IDE that I'll be using is this one right here. It's called Webstorm, and it is provided by JetBrains, if you guys know that company. It is a very excellent IDE. Currently, I am on the um, student license, so they do offer it free to students if you can apply for that program if it applies to you. Otherwise, I believe it is paid. Most of their stuff is paid. They might have a community version of one or two things, but if you can, I would recommend this IDE. It's one of the best, like honestly, for almost everything, especially Java. But just to show you how it looks, and also so you can know everything is. This is, all the code that we'll be writing right here. This is the terminal that will be running mostly, or that will be showing our output rather. Um, and this is just like the um, folder structure, but you don't need to see that, so that's fine. And that's basically the environment that I am running. So, getting back to the presentation. Today's goals, what we're going to learn in this presentation, is to understand what data structures are and what recursion is as well, and to understand why we need them and to understand when to use them. So starting off with data structures. So to give you a basic definition, a data structure is a special format for organizing or laying out data. And this layout will allow the structure to be in an efficient, or rather it will allow the data to be stored or accessed in an efficient way. And some solutions are more efficient than others. And to give you examples of some of the data structures, there's arrays, files, records, tables, trees, and so on and so forth. So why use data structures? Well, to be honest, no matter what problem that you are solving, in one way or another, you're going to have to deal with data. So the importance of data structures comes in these situations, in that you will know which data structure to use so that you manage your data effectively, as it's both beneficial to your program and to yourself if you can conceptualize the data that you're using in your program. And when to use them? Well, The short answer is all the time, because you are, as I said before, you will be working with data like in almost every program that you do. And the long answer is it kind of depends on what you're doing. So just in the context of depending on the kind of program you're making or the kind of like front end, back end, the situation that you're with, it's also change the kind of data structures that you use. So hopefully in this presentation you will get a kind of sense of when to use them, so you can use them at your own discretion. Yeah. Okay. So the data structures that we'll be covering today will include arrays / dictionaries, stacks, queues, and linked list. Just a quick note on why I said arrays / dictionaries. Just so you know, in other languages such as C# and Java and Python and so forth, the arrays and dictionaries are two different things and they work in different ways. However, in JavaScript, they're a bit more combined. Hopefully you'll see later on when I do the demonstration, but the way that dictionaries work and the way that arrays work in JavaScript is so similar that I basically just group them together. So, arrays. Most of you will probably, hopefully, be familiar with arrays, but basically an array is the simplest and most widely used data structure. Other data structures like stacks and queues are actually made from arrays. So they're basically like the building block of any program. And that image below over there is basically showing an abstract overview of how an array looks to like a human. It will look different to a computer, of course, but just to help visualize this, this is the picture of, let's say, 4 numbers. And you can see 1, 2, 3, 4, they're all next to each other. So in a computer, they'll all be next to each other in memory. And each container, so each of those boxes represents the data that's in the element of that array. So the whole thing together is an array, and each box inside that array is an element. And each of those elements are assigned a positive number called an index. And the index corresponds to the position of that specific element in the array. So the majority of languages do define the starting number as 0, but that changes from case to case. I think, correct me if I'm wrong, but I think Python does define it to start at 1. I could be wrong. I've never like done Python, but that's the only example that I can think of right now that makes arrays start at 1. But for all intents and purposes, most program languages will make arrays start at 0, including JavaScript. And the most common types of, or rather the 2 types of arrays are a one-dimensional array, as shown in this image here, and multi-dimensional arrays, which is basically just an array within an array. We'll do a demo later on just to conceptualize that. So this is just a brief summary of arrays, and yeah, basically everything that I said, the indexing of arrays, the fact that it's used to make other things like stacks and queues, and the 2 types of arrays that are most prevalent. So stacks. A brief definition of a stack is a data structure that stores the previous value in memory in such an order that the last one that went in is the first one that comes out. So if you see in this picture here, that is what a stack looks like. And the top, the arrow that's pointing in the top there, that's the last element that went into the stack. So it will be the first element that will come out. And a good example of this is the undo feature on most PCs. So like, for example, on Windows, it's Control Z, and on Mac, I think it's Command Z. And if you've ever used the undo function, you know that whenever you, like working in a text editor, for example, let's say Microsoft Word, and you type something or you paste a picture or you change the formatting, and you realize, wait, actually, I don't want to do that. I don't want to commit to this change. Then you can just press Control Z or press the undo button, and it will undo that last action that you did. And that's just a good example to conceptualize how a stack orders things. So the last thing that happened will be the first thing that you pop off the stack, basically. And yeah, just a quick summary on stacks. And the next data structure that is worth taking note of is queues. And a queue is basically a structure that stores elements in like a sequential manner. And the key difference between a queue and a stack or just any other data structure is that the queue uses um, the first in first out method. Sorry, I just realized now the slides might be a bit confusing, but ignore that part where it says the last in, first out method. That's a stack, actually. So the queue uses the first in, first out method, which basically, if you look at the picture down there, the front of the queue is where the element will be popped off, and the back of the queue is where you insert new elements. So a good example of this is like how queues work in real life. So if you get to the traffic department, for example, you want to book your learners or your drivers, or you want to renew your license, whatever have you. If you're the first person there and you're basically the first person in the queue, then they will service you first. And if you get there and you're the last person in the queue, then you have to wait for everyone else to do whatever they need to do, and then they'll get to you. So a queue basically works in that way, that the first element that was added to that queue is the first element that you can access. And queues don't have indexing. Actually, like I should have mentioned this for stacks as well, but stacks and queues can't be indexed in the way that arrays are indexed. And by that, I just mean you can't go directly to the element that you want. You have to traverse the queue in the order that it came through. So, sorry, just to go back a bit, stacks. So, for example, stack there, you see how I said the the last one that came in is the first one that comes out. So you can't actually access that number 1 at the bottom of the stack without first having to access 3 and 2. So you have to pop 3 and 2 off the stack before you can access 1. And similarly for queues, you have to traverse through the queue from 1, 2, 3, 4. You can't actually access 4 without first going through 1, 2, and 3. And yeah, that's basically queues. And yeah, that's a quick summary of queues for like to draw out the important points. And the final data structure is linked lists. So yeah, this is like the heaviest one, if I can call it that. But basically, a linked list is a chain of nodes. And to give you a definition of what a node is, it's similar to how arrays work, but not quite, in that each node, if you look at the picture there, each node consists of the data and a pointer to the next node. So, for example, if you have a linked list of strings, for example, and so the data in this picture would be the string. So let's say it's somebody's name, and then the pointer would just be like a reference or a memory address to the next node in that list. And conceptually, it's similar to a queue, but not quite, because it does have different ways of allocating memory, and internal structure is slightly different. And how the basic operations of insertion and deletion are carried out are also like a bit different. And yeah, that's basically how a linked list works. And there's the important thing to note as well is that there's a header pointer, which points to the first element of the linked list. And if the list is empty, then it'll point to null or nothing. And just a quick note worth mentioning is that with linked list, you get two main common types, which is a singly linked list and a doubly linked list. So the singly linked list is basically what you see now before you, the head being the front of the list, and with the data with the pointer and the last one pointing towards null. So that's a singly linked list, and a doubly linked list is basically the same thing. The only difference is that the each element has a reference to the next node in the list as well as the previous node in the list. So, for example, if you see that first head node in the list there, the one that has the head with the arrow pointing towards the data and the pointer, and the arrow from the pointer to the next node pointing towards that data. The only difference would be that if you can conceptualize this, is that a doubly linked list will have an arrow pointing from that second node to the first node. So it knows, so that second node knows what came before it and it knows what comes after it. But just to take note that it doesn't know, like any node in that list will only know what came before it and what came after it. So it won't know what the last thing is or what the, like, let's say fifth thing is if it's not next to it or before it. And yeah, that's basically linked lists. And oh, sorry, it's supposed to be a summary linked list. But anyway, moving on to the final topic we'll be talking about is recursion. So, um, yeah, recursion is a doozy. It is, it is like it still dribbles me to this day. But basically, to give you a brief overview, what recursion does, it's that it's a method of solving a problem where you break up the solution to that problem into smaller and smaller instances of the same problem. And yeah, this approach is useful because it can be applied to many different types of problems. And the main reason why recursion is used is because it saves the programmer's time rather than the machine's time in most cases. And by that, all I mean is that when you program a solution for recursively, so when you program a recursive solution, it's easier for you as the one making that solution, as the one coding and programming it, to actually code it in a recursive way. I'll show an example of this later on, but basically, it's easier for you to code that in a recursive way so that you understand what's happening and you are able to make a solution easier. Whereas the performance of that recursive function or method or whatever is not necessarily the most performant or efficient. Yeah, recursion can be like it's a double-edged sword. Like you need to know when to use it and when not to use it. But as I just mentioned now, the time to use it is mostly when you want to save the programmer's time versus like the machine's time. And for most recursive algorithms, there is usually an iterative or other solution that can be like employed. But those solutions are usually much longer and more difficult to conceptualize. So to give you an example, if you know what a Fibonacci number is, it's basically a a number that is made up of. Okay, it's kind of difficult to explain. I'll do an example like in the actual like Webstorm. But basically, the way that you go about programming a method to calculate the nth Fibonacci number, it's easy. It's so easy to do in recursion in terms of conceptualizing it. But if you were to do the same thing iteratively, it would be it would be slightly harder, like, and to be more lines of code, and it would be harder to like conceptualize like in your mind and on paper. And yeah, we'll do a couple of examples of recursion just so you can get a basic idea of how it works and when to use it. Um, and also just a quick note as to recursion in other languages. So in most languages, people might recommend that you avoid recursion because again, it does incur a lot of overhead in terms of performance and efficiency and everything like that. But in some languages, like for example, F sharp, where they optimize recursion using a method called tail optimized recursion, it can be helpful because that is a language that the primary way of iterating through things is using recursion. So I just want to get that in your minds. Like um, it's not a completely bad thing. So like you should basically just be aware. If you move on to other languages, be aware of how recursion is used in that language. Like the example that I just gave, F sharp tail optimized recursion is actually a method of recursion that is used quite frequently, and it's how most F sharp programmers will recommend you iterate over things. And yeah, that's basically the definition of recursion. And yeah, now to do some demonstrations on the things we just talked about. So let me just quickly share my screen with you again. Well, what? That's great. Sorry, give me a second. I think it's freaking out a bit. Whoa. Okay, there we go. Hopefully you can all see. And okay, so let's just run through some examples of some of these data structures that we talked about. So the first one that we talked about was arrays, right? So in JavaScript, how we initialize an array. Oh yeah, actually, I just wanted to make a quick note of this as well. You see this let keyword over here. I know some of you are used to var, which is I don't want to say perfectly fine, but just to so you know what's happening, the let keyword is basically like var, but the way var worked in JavaScript was, to say the least, let's just say not very nice. So what they did is, with the latest version of JavaScript, they changed it so that the let keyword is used instead. Okay, so moving on, let's initialize an array. I'm just going to call it my array and put the, let's say, okay, so I'm going to make an array of strings, and let me just put random names inside the array. So say John, Kim, and Bob. Oops, forgot my comma over there. Okay, so we have our array, right? And if you remember how I mentioned earlier on, let me just go back to this slide. Yeah, let me just show you this. Okay, so if you remember how I talked about arrays, they store data in a sequential manner like this. So that's basically what is happening here. This data, these strings, are stored in a sequential manner, and to access these elements in the array, we can simply just say my array and the index. So for example, um, index 1, which will give us Kim, and I'm just going to print that to the console. .log. Okay, cool. So if I run this, it should give us Kim over here. And yeah, that's basically how you access elements in an array. And if I wanted to change any one of these elements in the array, I could just say my array and then the index of the one that I want to modify. So if I want to change Kim to Jane, and then come here and print it again, I'll just keep that previous line just so you can see that it actually does change. Okay, so you see the exact same element has been changed. Okay, so I'm sure this isn't like hectically new news to you guys. You probably have dabbled with arrays a bit. So let's move on to slightly more complex methods. So stacks. Okay, this is where things are going to get a bit more hectic. So with the stack, the as I mentioned before, that JavaScript doesn't really have stacks built in. Like some other languages, like Java and C Sharp, will have a library like made by the actual like for in the example of C Sharp, it's Microsoft. They'll actually have a library that you can import. Comes with C Sharp. You can just import that, and you have stacks, and you can use them in your code. But with JavaScript, it's a bit different. All we have to work with is arrays. So what I did is I found this library so that we can actually use it here, JavaScript Algorithms. And I think I'll actually post a link in the chat just so you guys can take a look at it. It's a very, very nice library, GitHub library to basically experiment with algorithms and data structures and to get a understanding of how they work. Okay, so I'm just oh, okay. Sorry, I'm only seeing you guys' chat messages now. I will try to zoom in for you. Okay. Um, is there a way to zoom here? Let me see if I can change the view. I don't know if that helps. Can you please let me know if this is working for you? Okay, wait, sorry about that. Just having some connectivity issues. Um, okay, let me see if um yeah, this control mouse wheel up isn't working. I'm trying it right now. It's not zooming in. Um, but let me see if I can. Oh my goodness. See if I can change the view a bit for you. Mm, sorry, bear with me. Ah, okay, I think I have to go to the preferences actually. So let's change that. Uh, editor, font. Okay, let's say maybe 24. Yeah, that should be good. Supply that. Yes, no. Yeah, there we go. Please just let me know, like, is this okay? Can you see now? Hmm. Okay, cool. So I'm gonna assume that this is good for you guys. Awesome. And okay, so where was I? Oh yeah, stacks. Okay, so hopefully you had a chance to just quickly look at that library I just talked about just now. and I would attempt to use the stacks that they have defined in that library. So just going back to what I was saying earlier on, a stack is basically, yeah, just a element, I mean a data structure where the elements at the top are the ones that you access first, and you have to traverse this stack such that you can only access the top one first, and then like pop that off and it goes away, and then the next one, which is 2 in this case, will become the top, and then pop that off, and then 1 becomes the top of the stack. So let's see if we can make a new stack here. I hope this font is still okay. And also, just to let you know, this library that I was talking about, the JavaScript algorithms, I just had to import it so that it would work in my environment. But yeah, stack. Oh my goodness. Just find the stack here. Hmm. Oh my. I just realized it might be possible that they haven't implemented the stack. No, it's too bad. Okay, I'll come back to that. I'll like do it in a different way. But I do know for a fact that they do have a linked list. So let's just do that example for now. Okay. Okay. So we now have our stack. Oh, I haven't um, initialized it yet. But yeah, basically I mean, our linked list. Sorry, let me actually just change that so I don't get confused. We now have our linked list, and we need to add some elements in it so that we can have a head element, which will basically contain our yeah, our data and a pointer to the next element. And if there's no like other data, then to just point to null. Okay, I see someone is saying they can't see the code right now. Let me see if I just make it slightly bigger again. I think I'll make it like 30 or something. Should help. Yeah, editor, yeah. Let's make it 30. Yeah. Okay, nah, not too much difference. 32 maybe. Okay, yeah, there we go. Okay, I think this is pretty visible. So yeah, the um, the linked list. So let's just initialize a new instance of that. Just going to briefly look at the documentation because this is a relatively new library. So let's try adding something to this list. Dot add. Okay, cool. And we'll stick with our string example. So let's try adding John. And if we print this, oh my goodness, if we get the head element, which should be John in this example here. Let's see. No. Yeah, node value. Let's just run that. Hmm. Oh, okay. I see what's happening here. Ah, okay. My bad. I think it's not actually importing properly. Let me just fix that real quick. Uh, okay, yeah. In the meantime, I'm just going to quickly pull up this library that I was talking about. Okay, no, so there's the guy that actually made it. But yeah, so JavaScript Algorithms is a library. You can check it out on GitHub. And as you can see here, I'm going to go into the data structures because that's what we're focusing on. The stack, and yeah, there we go. He basically outlined what a stack is, how it works. And as you can see, the main methods that we use with a stack are pushing, which adds the elements to the collection. And remember how I talked about a stack pushes in a way that it's last in, first out. So as you can see here, let's say our stack has been initialized with just the number 1. So we push a 2 on it, and now our stack looks like this. It has 1, then 2. Push another one on it, and it looks like this, and so forth, so forth. Keep pushing stuff on, and this is how our stack looks like. So when you want to access these things on the stack now, you have to pop them. So that's the method that we use, and that's how we refer to it, popping. And when you pop, so let's say our stack looks like this with that number 6 at the top. When you pop it, you now have, you now take the 6 and you have access to the rest of these nodes, but you have to go to this one first. So you pop the 5, pop the 4, pop the 3, and so forth and so on. And by the end, if you pop this 2 and then you pop this 1, you will then have an empty stack. So this is a very nice like library or GitHub to use, and it shows the the ways to use it, and it's very nice. And I just want to quickly run through some of the methods that the most important methods for a stack. So with any data structure, really, you need a way to check if it's empty, and if this is if it is empty, it'll just return like a bool indicating like true or false. So if it's empty, then it's true. Otherwise, it returns false. And peek is basically just a method that gets you a copy of the element at the top, but it doesn't actually pop it off the stack. So this is important when you want to know what's on the stack, and but you don't want to take it off the stack. And yeah, we just talked about push and pop. That's how you add and remove stuff. And yeah, most data structures will have a method that will allow you to convert it to another data structure, which will usually be an array or a list. Like maybe they will support like stacks and queues and all this other stuff. But basically, um, the yeah, this is like the most common one to array. And yeah, I'm not going to run through all of them because I'm pretty sure you get the basic idea. But he has a lot of data structures. Like, to be honest, I didn't even know some of these existed, like Bloom filter. I'm pretty sure that's like a very specialized type of tree. But basically, the ones that we talked about here are the doubly linked list and the linked list, the queue, and the stack. Technically arrays too, but those quite basic, and actually uses them to implement these other data structures. So yeah, just check out that link, and you'll be able to see. Yeah. Okay. Cool. So this, I think my environment is not completely set up right, so I'm just gonna talk about recursion instead. And okay, yeah. So if you remember what I said about recursion, it's simply just a method of breaking down a problem into slightly smaller versions of that problem. And at the what makes recursion useful is that it's easy to conceptualize this, and once you get to the smallest, absolute smallest subset of a problem that you can have, then that will be your base case or your stop case, and you jump out of that recursion. So the most basic or not basic, but like the most common like example of this is a Fibonacci number. And just to give you a brief background for those of you that aren't maths majors, Fibonacci numbers basically as or a Fibonacci sequence is such that each number is the sum of the two numbers before it, starting from I think it was 0 and 1. So basically, fib 1 is equal to 1, and yeah, we're gonna code that now, so you can get a good idea of how they work. Okay, so I'm now going to declare my recursive function, just going to call it fib, short for Fibonacci. And okay, so we need the first thing that you do when you make a recursive function is just declare your base case or your stop case. And this is, like, as I mentioned now, the thing that will basically signal for you to jump out of that recursion and to stop this continuous like loop. So I think if what we do, so we say if oh yeah, x is the number the integer number that you give into this function. So let's say if x is greater than or rather, let's say if x is less than or equal to 1, then we just return 1, because basically, like, that's our stop case. I'm not going to dive too heavily into the Fibonacci math, but essentially all this means is that the smallest Fibonacci number you can have is 1, because you can't go like you don't go into negative Fibonacci numbers. So that's our stop case. If we get a 1, we stop recursively calling this function. Otherwise, assuming that um, x is greater than 1, we then say um, it's so Fibonacci is the Fibonacci of the current number plus the number before it. Hmm. Oh yeah, another thing I like about this IDE is that you'll see here it shows the name of the variable. So like, for example, if I call my variable number here, you can see that it pops up as number, and I find that pretty cool. So yeah, it's another nice little IntelliSense feature we have there. And oh, I forgot my semicolon. Must always remember semicolons, guys. Okay, so just a brief rundown. Um, yeah, if number is equal to just less than 1, otherwise, oh, sorry, I did it wrong. It's the other way around. So we return the preceding numbers before it. So yeah, the two numbers before it. And let's run this function, or rather, let's call it and give it a number of, let's say 10 for now. And then we run that. Oh, I need to get rid of this, actually. Oh, I forgot to change my X. It's now number. Okay. Let me just actually change that here as well. I should have refactored that actually, but anyway, things happen when you're coding. Yeah, that should be good. Let's run it again. My bad, I need to console log that. Yeah, there we go. So as you can see, the way that we calculate this answer 89, the Fibonacci of 10 is 89. So if you say 10 plus 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1, that should give you 89. And to show you this, let me just say at each, just before the recursion is called, I'm just gonna log it so you can see how the number is actually being calculated as we go. Number, and then let's run that. Yeah, so you can see like it's actually calculating the Fibonacci. So you can see it's going from 10 plus 9 plus 8 plus 7 plus 6 plus, all and all and all and all. And eventually, this is the answer it comes up to. So, um, how I mentioned earlier on that Fibonacci is easy to conceptualize, this is what I meant basically. Like you can see, this is just like what 1, 2, 3, 4, 5, no, 6. Okay, actually, let's call it 5 because this doesn't really like matter. But basically, 5 lines of code, and the actual logic behind understanding this Fibonacci or this recursive solution was easy for you to like grasp. Whereas I'm just gonna copy an iterative solution here for you guys. If you wanted to do the same thing iteratively, this is what it would look like. As you can see, this is what, like 1, 2, 3, 4, 5, 6, 7, 8 lines of code. I know 3 lines doesn't make like a super hectic difference, but when you start working on like bigger programs and like more hectic situations, like things like that can make a difference. Like 3 lines easily becomes 100. So basically, yeah, this is just to let you know how recursion works. And Fibonacci is an excellent example to get that across. Like it's one of the nice examples. And just to, we don't have time now to go through it, but just to give you another basic example that you can just conceptualize now is, how, let's say, for example, your folder structure. So let me see if I can just like get out of this, minimize that. Okay, so you see your folder structure, for example. So you have, let's go to my desktop. So you have your folder structure and you have all these other sub, and you also have some files as well. And if you wanted to traverse this, you would then have to, if you want to do it iteratively, you'd have to like basically make a for loop with the length of all the folders that you potentially have in here, and then you'd have to go through those folders and those folders and those files, and like it would just be a whole lot. Recursively, you would basically just you do the same thing, but it would be easier on your side to like conceptualize how you're going to do it. So you'd go to your desktop, and then you'd say, like let's say for example, you want to count how many folders or how many files are in the desktop. So that means you have to go to the desktop, count the files that are there, which are these ones, and you also have to go to the folders inside the desktop and count how many files are in this folder, this folder, this folder, and that folder. The fact that recursion makes that easier is like it will allow you to maybe write let's call it like 20 lines of code that will essentially um, help you conceptualize it in a way that you understand where you're starting from, and you're basically breaking down the counting into smaller subproblems. So you go and iterate all through all these elements inside your root like folder or your starting point. You'd count these ones, and then you'd say, okay, if there's any other folders, then do the exact same thing I just did for this folder and for that folder and for that folder and for that folder. And yeah, that's basically what recursion is. Um, Apologies, I couldn't fully show you the power of that JavaScript library that I was talking about just now. But yeah, it is a very nice library. Like I was checking it out earlier on, and like it's honestly awesome. I recommend you guys check it out just so you can like learn more about data structures. And yeah, so that's basically what I wanted to show you with regards to that. And yeah, this is basically the end of my presentation. If you have any questions, you can just pop them in the chat there, and I'll try answer them the best I can. And yeah. Jody, I see what you're saying about my wallpaper. Thank you. Okay, cool. So I'm assuming no one has any questions, and yeah, that about makes it for this tutorial on JavaScript, data structures, and recursion. I hope you guys learned something. And yeah, hopefully these slides will be up soon so you can check them out and revise them in your own time. And yeah, that's about it. Cheers, guys.